Once you start taking scientific measurements in class, it's important that you're able to comment on your accuracy and your precision. So I want to make clear what the meaning of these two terms are in this next video. So for the sake of this video, I'd like you to imagine that we are firing arrows at a target. And let's say that for one round of loosing arrows at a target, this is the pattern that we're able to achieve. Now, right away, you probably noticed that these 4 arrows landed pretty far away from where we hoped that they would have landed in the bullseye. In this case, I would actually say that we are not super duper accurate. So accuracy in this case means how close your measurement is to the real measurement or to the real goal, how close your arrows are landing to that target. Now, in this case, if you'll notice, if this had been the pattern of my arrows landing onto the target, they're really, really close to that bullseye. So in this case, this pattern would be accurate. Now I want to go back to the original pattern that you had seen on the screen before we completely move off of this topic. There is actually something really good about this pattern. You might notice that the arrows have actually landed fairly close together. So although we're not accurate, we're not really getting to the mark of where we wanted to be, we're at least being consistent, and that consistency is really important. That consistency we know in science class as precision. You would say that these measurements or these arrows are precise. Precision is a way of expressing how close your measurements are to one another. Let's take a look at another example. Let's say this was the pattern that my arrows landed on the target. In this case, you can see that the arrows are far apart from each other, and unfortunately that would mean that we are not precise. In fact, I'd even go so far as to say that this was probably a pretty bad round here, because not only are you not being precise and your arrows are far apart from each other, they're also very far apart from the mark itself, so we're also not accurate. Now, in this case, if you'll notice the second firing pattern, we're not only close to the mark, but the arrows are also close to each other. I would call this one accurate and precise. Accurate because the arrows are close to the bullseye, and precise because the arrows are close to each other. Let's take a look at this firing pattern. Now notice again, we're far apart from the mark, so I would go so far as to say probably not accurate, and the arrows are far apart from each other, so I'd say probably also not precise. So this one is neither accurate nor precise. Now it's all well and good to be talking about bullseyes and arrows, but I don't think that we're going to be allowed to practice archery on the inside of the lab room. What we do need to start taking a look at is real data that we might be collecting in the lab. So here's kind of a real life example. It's set up into 4 separate groups, A, B, C, and D. And what the task was to simply measure the volume of a liquid. Now the actual measurement is 68.1. That's your bullseye. And we need to comment on how well these groups did. How well did group A do? How well did group B do? C, and then D. We need to comment on both their accuracy and also their precision. Now you might be wondering, how am I going to comment on their accuracy if I have to do this with 3 measurements at the same time? And when you're dealing with a group of data, it's really important that you consider the average of that data when you're comparing it to the actual result, because sometimes your measurements might not be precise, but they might average together to be accurate. So what I'd like you to do now is to pause the video, take a moment, and see if you can define whether or not these groups are accurate or precise. So now that you've taken some time to think about whether or not these measurements are accurate or precise, I'd like to reveal my answers. So I calculated first the average of all of these groups, and I noticed that group A averaged to 41.3. Now that's not very close to 68.1, so I said not accurate. Also, when I take a look at the measurements, we're spanning from 78 all the way down to 2 milliliters. These measurements are very far apart from each other, so I also said not precise. Group B, The average was 68.1. Well, that's exactly on target, so I would say that this group is very accurate. Not only that, but they're all in the 68 range, so I would also say that this group is precise. Group B is kind of like the holy grail of measurements. Letter C, their average was about 98 milliliters. Now that's pretty far away from the actual measurement of 68, so they are not accurate. However, the measurements were at least close to each other, so they are precise. So at least they're doing something consistently. Letter D, their average came out to be about 66.8. Now it's not as good as group B, but it's still pretty close, so I would say that that group is accurate. Unfortunately, however, their numbers do kind of vary a little bit, and this one we might actually be able to argue about. I would say that they're not as precise as I would like them to be. Some others might argue that they are, but I'm going to kind of lean on the side of caution here and say that they're not precise, that these numbers are variable. Now, it's all well and good to be able to say the words accurate and precise, but it's a whole other to actually comment on this with numbers. So far, all we've been doing is using qualitative terms to say how well we're doing in the lab. It'd be really nice if we had something quantitative, and in fact, we do. So anytime that you sit down to take an assessment, usually at the end of it, you're given a grade, usually in the form of a test percentage. Now, in this case, this paper scored an 80%. That means that you're 80% correct, but you have a 20% error because it has to add up to that 100%. Take a look at this paper. This person scored a 50%. So they only got 50% correct, which means 50% of it was in error. And it's this error measurement that we actually use in science class. So we use a formula called percent error. This is a way of communicating the overall accuracy of a measurement, and it's a pretty simple little formula. Here it is. You kind of see that it's the part that gets subtracted away from 100. So if you scored that 80%, 20% is your error. So it does seem counterintuitive, but a low number for percent error is actually really, really good. We try and keep it low. Generally speaking, we want to try and keep our error definitely below 10%, and if you're below 5%, you're doing really great. A higher percent error can mean that you should probably go back and try the experiment one more time. Here's the formula for percent error. Now this one is using all of the technical jargon, and it can be a little bit confusing, and I'll break that down in just a minute. We do use the absolute value bars here. So sometimes when you're doing the subtraction on the top part of this fraction, it can come out to be a negative number. The absolute value bars mean just simply make it a positive value. Percent error is always presented as a positive value. And that's experimental minus theoretical divided by theoretical times 100. So in English, this is what it actually means. Experimental means you take your answer, the answer that you actually get in lab, and you're going to subtract that from the theoretical or the real answer. This is like the bullseye answer. This would have to be provided either by me or by a textbook or something that we're going to find in calculation. At any rate, it's found on a piece of paper. And then, of course, divided by that real answer again. It's almost like that's your total points. That's what the perfect answer would have been in a perfect world. And after we're done with that particular part of the calculation, then we multiply it times 100 to make it into a test percentage. Now, a couple notes here, because we've been talking about a lot of other things as well, including significant figures. So as far as significant figures are concerned, this 100 does not count towards significant figures. And that's mostly because this 100 is a counted number, and any counted number has an infinity number of significant figures, so it will not affect your final answer. The second thing I'd like to point out, we did talk about combined mathematical operations with significant figures, and percent error tends to be one of those that students traditionally have a hard time with. So I want to remind you here that the first thing that you're going to do is the subtraction up top. Now this uses the addition and subtraction rule. So you're going to look at the decimal place rather than the total number of significant figures in the number here. You're going to need to round using the addition subtraction rule here first before you continue with the division problem. Round it for significant figures. I think we should probably do a sample problem. So here is one. In an experiment, the density of iron was found to be 8.75 grams per milliliter. If the theoretical value, that's the bullseye number, is 8.71 grams per milliliter, what is the percent error? So the first thing I'm going to do is to write down my formula for percent error, and then I can begin to fill in my numbers. So the first thing I found is that in an experiment, I get 8.75. Well, that's my answer. That's the experimental number, so I'm going to fill it into that spot. The second number I find is 8.71, and they go ahead and label it as the theoretical value. Sometimes this is known as the real value or the true value or accepted value. All of those words will be given for that theoretical value. I'll go ahead and plug that into both the top and the bottom spots that are remaining. Now it's time to process the math. So I'm going to take the 8.75 minus the 8.71 and round that for significant figures first. That only leaves me with 0.04 on the top. That's one significant digit. Then I'm going to divide that by the 8.71 with 3 significant digits. But 1 significant digit divided by 3, I still can only keep 1. And then finally multiply it times 100. And then that's going to get me my final answer of about 0.5% error. In this case, because it's so low, I would have actually scored a test percentage of about a 99.5, and I think that would be doing a really great job. So hopefully you'll be able to achieve this pretty quickly and pretty easily. We will generally be calculating a percent error after most quantitative labs. That will be labs that involve collecting an answer that you can actually compare it to a true value.